Parietal, P-A-R-I-E-T-A-L. Temporal, T-E-M-P-O-O-R-A-L. Occipital, O-C-C-I-P-I-T-A-L. Now, frontal is motor function. Any motor command that comes out of the brain, any movement, this action potential originates in the frontal lobe. Frontal is motor. Parietal is sensory. Temporal is sound. Associated with hearing, sound. Sound or hear, I don't really hear. I'll put that here. H-E-A-R-I-N-G, hearing. And occipital in the back of the brain is associated with sight, vision. Now, those are the lobes of the brain. Those are the lobes of the brain, okay? Now, tell you about the Schwann cell. I'll do 2 or 3 more of these right here, and then we'll take a break, and I'll come back and finish it, all right? Now, the Schwann cell. Number 11. I got to go back to the neuron. I got to draw the neuron up here, okay? The neuron simply cannot function by itself. It is so far advanced that there's some functions that it cannot do. So it has helper cells, glia cells, they're called helper cells, in the nervous system. Some are in the central nervous system, some are in the peripheral nervous system. The Schwann cell is in the peripheral nervous system. Let me show you what that it is. Don't write anything down, not yet. So let me show you where it is, and then we'll talk about what it is and what it does, okay? So I got to go back to my neuron just for a few seconds. Number 1, I think it was. Name the functional cell. Yeah, draw and label a neuron, okay? I don't expect you to draw it. If you can't draw it, fine. If you can't, don't worry about it. Label the parts of it. The dendrites, the cell body, the axon hillock, the axon, and the teledendron. Name me the parts of it. But associated with the axon is a helper cell called a Schwann cell. You can probably guess the guy's name that discovered this right here. It won't Smith. All right. So here's the Schwann cell. Here's the Schwann cell. Here's the Schwann cell. All right. Now, I forgot to mention to you, these cells are microscopic in their width, but some of these damn things are 3 feet long. Curl your toes. Curl, flex, extend your big toes or your toes at all, okay? That signal originates up here in the frontal lobe right here. It travels down the cord. It's going to exit the cord about your waistline. Now that neuron that regulates the extenders and the flexors of your big toe is that long. The damn thing is that long. It's 3 feet long. And the taller you are, the longer that it is, okay? So anyway, these cells right here have to have something to speed up the conduction time of the action potential. A Schwann cell, the function of it, let me see. Describe the function. The Schwann cell insulates the axon. It produces a lipid, produces myelin. This is what I want you to write down. The Schwann cell produces myelin, which insulates the axon. M-I-L-I-N, myelin. Insulates, I-N-S-U-L-A-T-E-S, the axon. It produces myelin, which insulates the axon. That's the function of the Schwann cell. Now, if it's not insulated, this is no different than an electrical cord with a bare spot in it. It can short out. So just for the heck of it right here, and I don't think I have, oh yeah, I got in number 12 right there. And I'll wait and I'll cover number 12 here just in a few seconds right here, okay? So the Schwann cell produces myelin, which insulates the axon, which speeds up the conduction time of the action potential. I need that in your answer also, okay? Which insulates the axon, which, let's finish this statement right here, which speeds up, S-P-E-E-D, speeds up the conduction time. Of the action potential, which speeds up the conduction time of the action potential. Okay, now, the reason I want you to know that, there are a couple of diseases right here that disrupt the structure, the makeup, the function of the myelin itself. We call these demyelinating diseases. So demyelinating disease, defined demyelination, that's this rupture that's having abnormal myelin formed. That's good enough for me. It has abnormal myelin being formed. Now, these things can get so bad. Let me show you what I'm at right here. Normally, the action potential goes down this way right here. And this may take a fraction of a second to go back to flexing and extending your toes just for a few seconds right here. So flex and extend your toes right there. That signal takes about 3/10 of a second to go from your spine down to your toes itself. All right, so it's a fraction of a second that it takes for that signal to travel down that axon, which is 3 feet long now, 3 feet long, to the target right here. Now, if I had a demyelinating disease, the signal may not get there. So we have right here, let me disrupt this myelin right here, all right? Let me have a demyelinating disease right there. That signal may go there, and the damn thing may stop right there. The sucker may stop. At worst, it'll stop. But it might just slow it down and have it very, very aggravating for you to move at all. Okay, so define demyelination, name 2 demyelinating diseases right here. One is polio. Polio. What do they cause? They cause paralysis. Paralysis. The other is multiple sclerosis is the demyelinating diseases. So I want you to write down polio, P-O-L-I-O, and MS, MS for multiple sclerosis. I'll write it out, whichever one that you want to. They cause paralysis or partial paralysis. Okay, I want that they cause paralysis or partial paralysis. Okay? Now, let me touch on memory right here, and then we'll take a break. Memory. All righty? Get rid of this right here. Number 13. 13, okay. What I want to tell you is probably hogwash. It probably is, because nobody knows what memory is. 3 theories. Let me give you the furthest possible basis of memory right here is, well, let me back up. Memory is going to involve communication between neurons, because it's all you got in your brain. That's where the hell memory is. If I were to ask you to picture something that changed your life, or something that scared you, or something that really pleased you right here, you would have a vivid picture in your mind, a 3-dimensional picture. I know you do, because I do, okay? How in the world can we have memory stored in our brain? Okay, what are the possible explanations right here? One is, now this is a far-fetched theory, is that we grow more axons. That's what I heard when I was your age. And I believe it, because I bought into a lot of crap. Grow more axons. It ain't going to happen. But that was a possible theory of memory. Got to have a laugh at something right here. Might as well laugh at this. Grow more axons. Right. All right. Yeah. The second one right here. Let's increase the transmission, increase the release of neurotransmitters between existing neurons. Increase the release of neurotransmitters, the communication between existing neurons. Now we're getting to something that might have something to actually do with memory right here. So we're going to increase the transmission between neurons, all right? Increase, you give me it up here, I-N-C-R-E-S-E, up to you. Increase communication between B/T existing neurons. Oh, damn it. Between existing neurons. Okay, that means release more neurotransmitters, have more communications right there. All right. Now, another possible explanation right here is that we involve more senses. I'll explain it. Something I want you to get out of this. This may help you right here. Involve more sensory input. That's a better phrase right here. Involve more sensory input. I-N-P-U-T. Input. I remember when I was studying, especially calculus. I took electives in calculus down in Georgia. Well, I needed a science, and I understood calculus, so I liked it. And then when it came time to a formula right there, instead of me just sitting down and looking at it, I would write it out. If that didn't work, I would read the damn thing. So I would have sight, I would have audio, and I would have visual. Those are the inputs. It's the only thing we got right there. So if we have more inputs, if it's something difficult for you to learn, read it aloud. Get into a room, get into a space right there where you got some private time, read it aloud. And you've got your hearing involved. You've got a different region of the brain involved. Okay? Now, that finishes number 13. There was a movie called, with John Travolta. Oh, hell, it escapes me right now. Phenomenon, that's it, Phenomenon. You may have heard of it. It probably came out about the time you were born. Probably did right there. Anyway, John was just a good old country boy, and he was struck by lightning, or so the movie showed right there. And then all of a sudden, he was brilliant. He learned Portuguese, the language of Portuguese, in 7 minutes. He learned the language in 7 minutes right there. He could solve the most complex problems. And he couldn't do this before the lightning struck right there. Well, it come to find out that John Travolta had a tumor, had a glioma. Now, the glia cell is a helper cell in the central nervous system. The glia cell in the brain is an astrocyte. So more specifically, he had an astrocytoma. So he had more communications between more nerve cells. And that's one reason I wrote down this second one up here, increased communication between neurons, between existing neurons. And maybe memory is that way, I don't know. But anyway, in the movie, John died from a brain tumor. It had nothing to do with